PCB Foundations, by Paul Taubman and Sean Kelly. Presented by 9.Connects. Chapter 8. Schematic Library and Symbol Creation. 8.1. Introduction. The importance of component libraries and library management was discussed in the previous chapter. This chapter will focus on the schematic library and the use of symbols in the schematic editor. 8.2. Schematic editor versus schematic library editor. The schematic editor will be the main platform for capturing the design of the circuit. However, it is the symbols that are the very foundation of the schematic drawing. Without the symbols, the schematic editor is nothing more than a glorified drawing tool. Components are represented on the schematic in the form of symbols. Symbolic representations can be considered a language, developed over the decades of electronic design as new components have been introduced. The symbols are more than just graphical representations, they also contain information that is not generally displayed on the schematic itself. This includes parametric information pertaining to component characteristics, such as value, tolerance, temperature rating, etc., and information that would allow the purchasing of components, such as the manufacturer's name and component part number. It also includes a link to the footprint, and may also include other models such as simulation and signal integrity models. Most EDA tools will provide a basic library of well-known component symbols, though such libraries will not always provide a specific manufacturer name or part number. Generic symbols and footprints are provided with the assumption that the user will copy them for use in a real component. 8.3. Purpose of symbols on a schematic. There are two purposes for a symbol on a schematic. 1. To assist with the creation of a netlist. And 2. To assist a human in reading the schematic. Consider an extreme example of a rather useless symbol, along with a rather useless corresponding footprint. Granted, footprints are another library, but to understand the role of the symbol, we need to bring the footprint into this discussion. More details about the footprint will be presented in a later chapter. The purpose of showing this extreme example is to drive home an important point. The footprint shown here is as ludicrous as the symbol being shown. But as far as the EDA tool is concerned, there's nothing wrong with the symbol and the footprint presented. The symbol has 2 pins, and the footprint has 2 pads. Furthermore, the numbers assigned to the pins match with the numbers on the pads. If we were to place the symbol on the schematic and then push this information to the PCB layout tool, the tool will not complain. What the EDA tool is providing is an automated way of creating and passing netlist information from the schematic to the PCB, based on the pins of the component. The EDA tool does not know anything about the guts of the component, nor how it works. The tool is only concerned with the pin-to-pin connectivity. Though the purpose of the pins and the symbol are for netlisting, the symbol's graphic is for human readability. It is nothing more than a graphic that is displayed, as far as the EDA tool is concerned. In fact, one can have a symbol that has nothing more than a bunch of pins, and the tool will be perfectly content with it. As for the PCB footprint, it provides contact points for the components that will be soldered onto the PCB. If this is drawn incorrectly, there will be major issues to deal with during the assembly phase of the project. However, in going back to the overall objective of the EDA tool, it has no concern or clue that it was drawn incorrectly. The fact that the pads exist, and that the assigned pad numbers match the pin numbers of the symbol, is all that matters to the tool. Therefore, the drawing of the symbol and the footprint require diligence by the designer. It is also strongly suggested that at least one other person verify the pinout of the symbol, and the dimensions of the footprint. 8.4. Symbol drawing styles. Notice that there are different styles of schematic symbols. There are 2 general types that have evolved over time. The first style is based upon discrete components. In the figure above, there are several discrete components, such as capacitors, C1, C2, and C5, resistors, R2, R8, R9, and R10, and an LED, D1. Though there are exceptions, a discrete can be loosely defined as a single-function component. Two-pin devices, like resistors and capacitors, are great examples. However, even devices like logic gates and amplifiers, usually 8 pins, are also considered to be discrete components. The second style is commonly used to represent components with a number of pins, such as IC, integrated circuits. In the example above, U1 and SW1 components are represented in the IC style. For the first 60+ years of circuit design, there were no ICs. Circuit design was accomplished through discrete components. It was only in the 1970s that ICs became widely available, since they allowed for more functionality in a small component package. As the IC became more common, a gray area emerged regarding their symbolic representation. For instance, a logic chip such as the 7400 quad NAND gate could be shown on the schematic as either 4 separate symbols, or represented as a single IC chip. The use of the 4 separate gates allows the user to follow and understand what the circuitry was trying to accomplish. This practice of using discretes to help the user analyze the circuit is still used in power and analog circuitry. The use of the IC style symbol has two purposes. The first is to simply fit the design onto the schematic, especially with components that have pin counts in the hundreds or thousands. Second, with the amount of functionality in today's ICs, the IC can be considered a system all to its own. Therefore, its individual functions cannot be graphically represented, so the symbol is simply providing the pins for netlisting. 8.5. One symbol, multiple graphics. ICs and certain discrete components are not well served using a single graphical representation. For example, the Micron SD-RAM, Synchronous Dynamic Random Access Memory chip, would require a massive sheet size to represent all 896 pins. To make use of smaller sheet sizes, library editors allow the component to be represented by multiple graphics. These are commonly referred to as multi-module, or multi-part symbols. A graphic that is a part of a multi-module symbol is called a submodule. This allows the different parts of the component to be placed on various schematics, while still being represented as a single footprint on the PCB and as a single line item on a bill of materials. In reference to the Micron SD-RAM submodules shown here, all 11 graphical representations need not be on the same schematic. In the symbol library, they are represented as parts of a particular symbol for the Micron chip. 8.6. Consistency in symbol graphics. Discrete components have taken on several symbolic representations over time. If one were to look at the ANSI 315 standard of 1975, one would see several resistor representations. In fact, there are currently two competing standards for discrete resistors. In the example provided, one resistor symbol is based upon the ANSI/IEEE standard 315, which is widely used in North America, while the other is based on the European IEC standard. Neither one is wrong. However, it is important that whatever standard is being used, the library and schematics need to be consistent with it. 8.7. Symbol creation. Mentioning it once again to drive the point home, the most significant problem with component libraries is a lack of consistency. A good library has a common look and feel, and contains a complete set of parameters and models to fully describe each part. The issue is not always about doing it wrong per se, but being consistent with the way each aspect of the component is addressed. There are a number of aspects of the component that need to be consistent, such as pin color, label font, pin length, color of the symbol, color of boxes, names of the parameters, format of the values in the parameters, etc. Please refer to the appendix for a detailed list. 8.8. Start with the datasheets. Prior to drawing any symbol, the very first document that should be obtained for the component is the datasheet. This should be without exception. In fact, many companies will not add a component to their master purchasing database without the datasheet. The datasheet is proof of the component's existence. Component datasheets provide what is needed to draw both the symbol and the footprint. There may be more than one datasheet, depending on the complexity of the component and the component manufacturer's way of handling their documentation. In some cases, the datasheet is more like a data book, with several hundred pages. All datasheets associated to a particular component should be added to the symbol as links or references. This will allow the individuals testing and/or debugging the circuit to quickly obtain the datasheets as needed. Since component obsolescence is commonplace, datasheets should be saved to a shared drive for current and future reference. One of the first things a manufacturer will remove from their website upon declaring EOL, end of life, are the datasheets. Linking a component to datasheets on a website is simply not recommended due to the ever-changing nature of websites. 8.9. Component naming. Let's start with an everyday example. When a clerk scans the item that you purchased, the system matches that scanned code to a record. That record contains the name of the product, the cost of the product, and whether it is taxable, depending on the municipality. The record must have a unique identifier, otherwise the clerk would have to sort through a list of products with the same identifier. In fact, in every database on the face of the planet, every record within a database must have a unique identifier, also known as a key field. The same concept holds true for libraries. In this case, we do not call them records, rather, we call them components. In symbol-centric libraries, the component's name is the component's unique identifier. It is to note that component-centric libraries also benefit from unique component names, but uses other means to prevent duplicates. The name can be used to describe the component directly, or could be a standard part number convention that an organization agrees to. This allows the designer to search a list of symbol names for components of interest when designing the schematic. It is okay to have long symbol names, as long as they are consistent with the information being provided. Consistent naming allows the designer to sort the symbol names for components of interest. It's one thing to have a list of 3 or 4 dozen components, it's another when there are hundreds or thousands of components in the library. There are various ways of naming a component. The following convention is simply a recommendation to help the designer sort and find components of interest, based on some key characteristics of the component. The method being described starts with the general details, and progresses to specific details. General component category. Purpose category. Manufacturer's name. Manufacturer's part number. General component category. This is a high level of sorting components. Components generally fall into one of several categories, as listed here. Discretes, single-function components that contain a number of unique characteristics that set it apart from other discretes. For example, resistors, capacitors, diodes, BJTs, and op-amps. ICs, components that provide complex functions, and cannot be easily represented by traditional symbols. They are represented as a box with pins. For example, processors, oscillators, regulators, and FPGAs. Mechanical, components that have no footprint and/or electrical function. They provide the board a needed mechanical aspect. For example, handles, spacers, heatsinks, and stiffeners. Connectors, components that allow for electrical connectivity to other devices outside of the PCB. For example, DB9, terminal block, USB port, and Ethernet port. Embedded, components that are embedded into the PCB. For example, test points, fiducials, and wiring pads. Purpose category, types. The general category certainly helps to provide some high-level sorting, however, most component categories need additional sorting. For a discrete like a resistor or capacitor, there can be multiple types of these components. For example, TVS, Schottky, Zener, and tunnel, are just a few of the different types of diodes. Since each of these provide a different functionality, they need to be part of the name. ICs also need to be further sorted. Though this list is not definitive, it provides some guidance. Digital ICs, components that are digital in nature, both input and output. For example, logic gates, U processors, and FPGAs. Analog ICs, components that are analog in nature, both input and output. For example, op-amps, regulators, and oscillators. Mixed ICs, components that provide both analog and digital signals. For example, DSPs, A to Ds, and D to As. Manufacturer's name and part number. The manufacturer's name and corresponding part number and the name of the symbol allow for a unique name, which is required in the library. When it comes to the manufacturer's name, be consistent. For example, Texas Instruments is also referred to as TI. Use one or the other, but not both. Otherwise, it lessens the ability to sort the components in the library. Represented on the top of this slide are examples of a simple list type. On the bottom, there are examples of a more complex scheme that allows for sorting based on component category. 8.10. Default grid. Though one can change the grid to make very detailed symbolic graphics, it is imperative that one places the pin's electrical hotspot on the grid. The hotspot is defined as being the tip of the pin primitive. This is what the EDA tool is going to locate and use when it is analyzing the design and generating a netlist. Since we are working in a schematic environment, the concept of dimensions is not applicable. Therefore, there is no valid reason to change the default grid in the symbol or schematic editors. If one decides to make use of a different grid, which is highly frowned upon, doing so may prevent the use of components provided by the EDA company, or by colleagues. The footprint library is different because one must draw the copper features to real dimensions, however, this is not the case with symbols. 8.11. Symbol sizes. Although schematics are supposed to be dimensionless, we must draw something that is big enough to show all the pins and labels. The IPC 2612 specifications outline suggested symbol sizes and pin separation. 1. The pin should be 200 mils or 300 mils in length, and separated from adjacent pins by 100 mils. 2. The pin number should be 60 mils in height to easily fit between pins. 3. Allow the box to extend past the topmost pin by 100 mils to 200 mils, and the same for the bottommost pins. 4. If there are more output pins than input pins, then the greater pin count drives the overall symbol size. Following these simple rules will allow your symbols to match pre-built library symbols for the ANSI B and C size formats. Note that 1 inch is equal to 1000 mils. The mil is commonly used in PCB design. A B size sheet is 11 by 17 inches, a C size is 17 by 22 inches. Business printers can handle B size sheets. C size or larger will typically require a plotter or large format inkjet. 8.12. Minimize lead length. Though the IPC 2612 recommends pin lengths of 200 mils or 300 mils, the pin length can be 100 mils. Discretes with long leads make it more difficult to maneuver the wiring around these components in the schematic. 8.13. Symbol origin consistency. A symbol editor will provide an origin for the component. Some designers may build the symbol symmetric to the origin, while others may position the graphics of the component to a certain edge, corner, or pin. Regardless of how it is done, consistency throughout the libraries is highly recommended. The origin serves as the reference for the cursor when placing the component onto the schematic. More importantly, if there was a change to the component graphic in the library, that consistency will prevent the part from moving in the schematic during the update. In a similar fashion, the component orientation should be kept similar. If the resistors are going to be drawn in a vertical fashion, the capacitors and other discretes should follow suit. 8.14. Display pin numbers. Pin numbers should be displayed. This is especially true in IC symbols. It does not hurt to hide them for discretes, except for diodes, but show them if it does not clutter the schematic. If one runs a SPICE simulation, the pin numbers align to the model's pin number. Most importantly, the pin number will match with the pad number of the corresponding footprint. Note, there is not any consensus on assignment of pin number to the anode/cathode of a diode, so it is important to verify on every diode that it matches the footprint. 8.15. Display pin names. Pin names are very beneficial, especially with IC-style components where the graphic itself does not provide functional information. The pin names can give hints as to the functionality of the symbol. For example, if a component has an enable, a read-write, data, and address pins, it is likely a memory of some sort. One should avoid the use of metacharacters in the name. Alphanumeric characters are A through Z, both upper and lower case, and the numbers characters 0 through 9. All non-alphanumeric characters are metacharacters. Here are examples of metacharacters found on a typical keyboard. All metacharacters have specific meanings or directives in both programming languages and in operating systems. A function or feature of a tool that was not robustly programmed can be tripped up by these characters. If one is familiar with programming, one should treat pin names the same way one would create a variable name by sticking to alphanumeric characters. The only exception to the list of metacharacters that one can utilize is the underscore character. This character has traditionally been used as a substitute for a white space. Though newer OS systems seem to handle white spaces well, the white space has traditionally been used as a record separator or delimiter in programs. Modern programming techniques, where a name requires 2 or more words, the practice is to concatenate the words with the first letter capitalized in each word, as seen in this example, processor enable. 8.16. Don't make up symbols. Every discrete has a symbol. If it is not declared in the IEEE or IEC standards, look on the web. Even bizarre components, like the Muller C element and the memristor, have a symbolic representation. If a symbol cannot be found, default to the IC symbol style. 8.17. Hidden pins. Hidden pins were an attempt to deal with power and ground when designing digital circuits on the gate level. This practice was prevalent in the 1980s, but was replaced with the use of more complex digital ICs. As mentioned throughout these chapters, the IC symbol style relies on the pin names and their corresponding numbers, thus there is no longer the need to hide pins. Unfortunately, the practice of hidden pins is still allowed, and it should be avoided at all costs. Note, legacy libraries may have parts with hidden pins. If accessing these libraries, review the pins. Consider a typical digital logic component, such as the 7408 AND, which consists of 4 independent logic AND gates, a power pin, and a ground pin. The big question is where to put the power and ground in a multi-module symbol for the 7408 AND device. If this is not connected in the schematic, it will not be connected in the netlist that is passed to the PCB layout. To complicate matters, not all the logic gates need to be used since they are logically independent of each other. Note, it is a good practice to ground the inputs of logic gates that are not being used. This reduces noise and power consumption. It is recommended, but not required. There are different ways to handle this. In the example here, U2D contains the power and ground pins. However, if the user forgets to place U2D because they only needed 2 of the 4 gates, power and ground would not be connected to the component. In the past, the symbols power and ground were almost always labeled VDD and GND, respectively. However, the complexity of newer designs often includes different voltages, and in some cases, different grounds. As a result, there is no guarantee that the label VDD or GND will be used in the design. If there is a label mismatch between the hidden pin name and the name given to the power signal on the schematic, the pin will not be connected in the netlist. Therefore, do not use hidden pins. If hidden pins are not recommended, what would be the best way to handle power and ground? One recommendation is to create another submodule that is dedicated to the power and ground pins. The advantage is that the power and ground pins are visible, and more importantly, are not attached to any particular gate. In addition, since decoupling capacitors between power and ground are often used for each individual IC, having a separate power/ground submodule symbol allows one to connect the decoupling capacitors, without involving one of the logic gates. The next recommendation goes against a current practice to reserve power and ground for the last submodule. Like the first example shown above, this could be overlooked if we only need the first two logic gates. Therefore, it is recommended that the power/ground submodule be the first submodule. In addition, we can take advantage of the fact that we can overlay symbols on top of each other in the schematic editor. 8.18. Inputs and outputs. Since schematics are dimensionless, the pins should be arranged to allow the schematic to be read like a book, from left to right. Therefore, inputs should be on the left side with the outputs on the right. Bidirectional pins can be on either side, depending on their purpose. For example, if a bidirectional pin is communicating with a component on its left side, then the bidirectional pin should be placed on the left side of symbol. Though it is becoming more popular, it is suggested that pins not be placed on the top or bottom of the graphic. Instead, it would be beneficial to break up the component into several submodules, thus allowing the designer to group pins based upon functionality. Drawing an IC symbol based upon the order of the pin number is acceptable, though once a component is placed in the schematic, pins may have to be moved by the designer to better handle the flow of the circuitry. More discussion about the circuit flow of the schematic will be introduced in a later chapter. In many cases, a balance can be achieved to have both a grouping of functionality along with providing a flow that will help minimize the need to move pins in the schematic. 8.19. Pin type. Pin types should be set for each pin. This enhances the readability of the schematic. For example, if a pin is known to be an input, it should be declared as such. The same holds true for outputs, bidirectional pins, power, etc. An arrow will be added to the pin to show the direction, if applicable. By declaring the pin types, the schematic editor's ERC, electrical rule checker, can perform electrical connectivity checks for potential electrical shorts or conflicts. Some designers don't use them because the ERC will declare false positives. For example, when an input is connected to a pull-up resistor, you will get a no driving source error in the Altium Designer EDA tool. The result is either that portion of the rule checker gets disabled, or a real error gets buried in a list of dozens of false positives. 8.20. Power and ground placement. By placing the power and ground pins on equal and opposite sides towards the bottom or top of an IC, the designer can easily attach decoupling capacitors to the IC. This keeps the schematic from looking messy. 8.21. Chapter Summary. The creation of symbols is a necessity to complete a schematic design. With over 1 billion components on the market, symbols will have to be made. Though some companies have a dedicated library group for this purpose, most designers will have to create symbols. The symbol has two purposes. It is vital for the netlist, which is used by the PCB layout to assist in copper connectivity. It is also used to make the circuit human readable. As components have evolved from discretes to ICs, the need to represent these components has changed as well. Discretes have specific representations, while ICs are best served by their pin number and name. There is a great deal of thought that must go into the creation of a good component symbol. If you work for a company that has a dedicated librarian, consider yourself fortunate. Make every effort to cooperate with this individual, now that you know the effort it takes to put together a good library. If you are the lucky one who is going to put together a library, either for yourself or for a group, be methodical and consistent. In the appendix of the physical copy of PCB Foundations, a checklist has been provided to assist in the component creation process.